sort of a vague plan is that today, in the first 2 lectures, I really want to talk about incoherence and tell you a couple of theorems and prove a couple of theorems that I think really gave me an in into the subject and will really allow you to prove a lot. And then in the last lecture, I want to give you a proof of coherence, and I want to prove a theorem that, in my mind, the proof that's in the original paper is sort of quite hard to read because maybe times have moved on slightly and we think about things in a slightly different way. So I sort of want to give you a streamlined proof there. Okay, so let's begin. So a great reference for everything that I'm going to talk about is a very recent survey, which has just been made accessible on the website for this conference by Danny Wise. So it's called An Invitation to Coherent Groups, and it's going to be published in a volume called What's Next? Mathematics After the Legacy, after Bill Thurston, or some sort of words to that effect. It's really great. If you're watching this live or you're watching this on YouTube and it wasn't too long ago, this survey is really recent. It's from, I think it was written last year. And so the results in it are really up to date. It really contains a good survey of how coherence is now. It's not old, it's not outdated anyway. Okay, so let's begin. So I'm going to begin quite basic. So just with definition. So a group is coherent if all its finitely generated subgroups are finitely presented. Okay, so somebody who is maybe, perhaps my upbringing in group theory was via combinatorial group theory. This is sort of a very natural thing to me. Okay, if you have a finitely generated subgroup, how are you going to describe groups? Well, one natural way is to describe them via a finite presentation. And so if you want to describe a finitely generated subgroup, perhaps you could do it via a finite presentation of that subgroup. Okay, and so a group is incoherent if it's not coherent, or if there exists a finitely generated, not finitely presented subgroup. Okay, and so in this lecture, so the first that when you meet, perhaps when you first meet groups, you meet finite groups, and they're obviously finitely generated. And then you meet some finitely generated infinite groups. And then, maybe a first exercise is to prove that something like the infinite direct sum of the integers is not finitely generated, or prove that something's not finitely generated. Okay, and so for that, you need some invariant, and it's sort of a non-trivial task. And so we're going to need something for finitely presented. Okay, and so I just want to sort of maybe remind you all, but the thing that we're going to talk about today quite a lot, and the thing that's really going to be worthwhile is a classifying space for a group G. So a classifying space is a CW complex X such that the fundamental group of X is G, and the higher homotopy groups of X. Actually, let me say it like this. I think that I decided. Such that the universal cover is homotopy equivalent to a point, okay? And so if you never come across the notion of, so this is, you're given a group and you want to associate some natural topological space, okay? And so if you've never come across classifying spaces before, then there are 2 exercises that you should do, okay? And these are both on so there are exercises on the website, and I've written all of these things down. So firstly, classifying spaces exist, right? So if you hand me a group, I can construct a topological space with these 2. I can construct a CW complex with these 2 properties. Okay, and secondly, a useful thing for us is that they are unique up to homotopy equivalence. Okay, so maybe just a quick example. For Z, you have the circle, and for I'm struggling to think of examples where the definition of the example isn't just that you have it's the fundamental group of its classifying space. Or maybe a sort of harder example is for Z mod 2Z, you end up with RP infinity. Okay, and so you could build different classifying spaces. For instance, you could just take the product of these classifying spaces with an interval, and that gives you something which has the same properties but is not homeomorphic. Okay, but up to homotopy, you haven't done anything. Okay, and so there's a nice topological notion of finitely presented in terms of classifying spaces. So a group is finitely presented if and only if there exists a classifying space with finite 2 skeleton. Okay, so this is you've taken, so for me, so maybe, you know, finitely presented from a combinatorial group theory perspective is that G is isomorphic to a free group modulo the normal closure of R, where X and R are finite. Okay, so this is an algebraic definition. It's a quotient of a finitely generated free group by a finitely normally generated subgroup. Oh yeah, that's a good question. So R is just a subset of the free group on X. And I shouldn't have used X. Okay, so it's just that you have finitely many generators and finitely many relations. Okay, and this is a topological notion. Okay, so instead of, you could throw away this algebra and you could just say, well, let's look at the fundamental groups of spaces with finite 2 skeleton. Okay, and so just sort of a brief idea of the proof. You know, so for one direction, you really just build the space. So you build the Cayley 2 complex for your presentation, AR, and then complete in some appropriate sense to a classifying space. Okay, so you do the correct thing at dimension 2, so you build a space with your group as its fundamental group, and then you add higher dimensional cells, so cells of dimension 3 and higher, to make sure that the universal cover is contractible. Okay, and by doing this, you've constructed something with a finite 2 skeleton. Going the other way, you want to present G as using 1 cells as generators, 2 cells as relators. Okay, so right, if you want to, I mean, a sort of very small exercise is that if you have a CW complex, then you can, or if you have a simplicial complex, then its fundamental group is generated by the edges, and you kill all of the edges in a maximal tree, and you have the boundary of 2 cells as relations. Okay, so this is sort of similar to Riley's talk when she presented the fundamental group of a graph of groups. It was sort of generated by the vertex groups and the edges, and you were killing all of the edges in a maximal tree, and you had these sort of extra relations coming from the edges. Okay, so it's sort of similar but slightly different in this case. Okay, and so one nice thing about defining it topically in terms of a classifying space is that it allows you to define a new invariant of your group G. So namely, we define the homology of a group. So if we have a classifying space for a group G, we define the homology of G as the nth homology of G is just defined as the nth homology of X, and just to be very specific, with coefficients in Z. Okay, so for those of you who've come across, so there are sort of more exotic homology theories that you could take into account on the right-hand side. And so you could define the homology of G with coefficients in some different ring or some different abelian group. Okay, you can also define you know, when you really get into it, it turns out that you can define homology of a group with coefficients in a module over the group ring. Okay, and this allows you some more complicated definition. I'm not going to talk about that. If you want to talk about that, I'm very happy to, but we'll save it for the office hours. Okay, and so the point is that because X was unique up to homotopy equivalence, this is an invariant of G. So by homotopy invariance of X, this is an invariant of G. Okay, and then so the nice thing about this invariant is, you know, when you want to prove that a group is finitely generated, one thing, well, if you want to prove that a group is not finitely generated, one thing you could do is prove that it has an infinitely generated quotient. And maybe the easiest infinitely generated group was the one I said at the beginning, was maybe a direct product of copies of Z. And so if you can prove that a classifying space has infinitely generated first homology, then you know that your group is not finitely generated. Now that is an equivalence. And once again, we can talk about that during the office hours if you like. But this also gives us something for finitely presented. So sort of an elementary, well, so a really easy proposition is that if G is finitely presented, then the second homology, H2 of G, is finitely generated. Right? Because H2 of G, so the second homology of G is the second homology of a classifying space. I'm going to drop the Z coefficients throughout the rest. So the second homology of G is the second homology of the classifying space, and we can take X with finite 2 skeleton. Oh, that's not what I wanted to do. Sorry about that. Okay, so we can take X with finite 2 skeleton, and then H2 of X, right, just by definition, is the kernel of the second boundary map modulo the image of the third boundary map. And this, there are finitely many 2 cells. So this kernel is a subgroup of Z to the n for some n. And so it's a finitely generated group. And so you're looking at the quotient of some finitely generated abelian group. Okay, so this is going to be the invariant we use today. This is going to be, so if you want to show that something's not finitely presented, so, you know, the contrapositive to this is that H2 of G infinitely generated implies G not finitely presented. And actually, I mean, it's a really interesting question about whether, you know, this is an if and only if, and the answer is no. And there's been a lot of interesting work in that. And once again, I'm going to try and link to some resources of where you could go after this, and that's going to be one of them. Okay, so so great. Now we have our invariant. Now we're actually going to be able to prove that something's infinitely presented. Okay. So how am I going to construct my group? Okay, so I'm going to sort of construct it a little bit out of the blue. Okay, and this is sorry, I'm going to construct my not finitely presented group a little bit out of the blue. But then we'll see where it comes from, and we'll really be able to see that it's actually very natural. Okay, so let's start. So what I want to start with is I want to start with a free group on 2 generators. Okay, so throughout L is always going to be isomorphic to a free group on 2 generators. And throughout, I'm going to sort of change what I label those generators to make presentations easier to write down. Okay, so they're going to be, so throughout they're going to be either A and B, S and T, or X and Y. And I think those were the only 3 choices I made, but just to point out, you know, it's a free group on 2 generators. It doesn't matter which alphabet you take. as long as the cardinalities are the same, then the free groups are isomorphic. And so if we take L to be the free group on two generators, then there's a map to Z, which takes both of these generators to 1. And so a proposition is that if you look at the kernel of this map, then K0 is not finitely generated. Okay, in fact, K0, so you can write down a generating set, you can write down exactly what K0 is. K0 is free on, let's say it like this, K0 has a free basis a to the n, b to the negative n, n in z. Okay, so you should check that. So there are sort of two things. There are two things to check here. One is that the things I've written down really do generate K0. Okay, and that's really not hard. You can just sort of you sort of go by induction on the length of a word. The other thing to check is that this really is a free basis, but where is it coming from? It's coming from topology, and so the thing to do is look at the covering space. So Radeke talked about covering spaces of arrows, and so you can look at the covering space corresponding to this subgroup, and what it looks like is it sort of looks like a double helix. Is that? It looks like a helix, right? And so here's your covering space, and you know, you can label these edges by A and B, and it's normal cover, so it doesn't matter which base point you pick, and it goes on infinitely in both directions. Okay, and so it's quite easy to see that the sort of the number of loops in this cover, I mean, there are infinitely many loops that are all independent of each other. And in fact, this covering space tells us more, or this having a free basis tells us more. So what we're actually going to use about this is not only is it infinitely generated, but you can see this infinite generation at the level of homology, right? So this fact, so if you abelianize the free group on X, then you get the free abelian group on X. And so this fact tells us that the abelianization of K0, or the first homology, is equal to a direct sum of copies of Z, one infinitely many. Okay, so so it might be easier to think of this as sort of an integer's worth, and the nth copy is generated by a to the n, b to the negative n. But I didn't want to write the integers too many times, so so this is what I'm sticking with. Okay, so it has infinitely generated homology. We can see that it's infinitely generated, and we can see it at the level of homology. Okay, and this is going to come back in a second when we build our group. So, okay, so now, so let's just pause for a second. So I've taken a free group on two generators, and I've built an infinitely generated subgroup. Now, the great thing was that last week, Riley gave us a way of, if you take a group and a subgroup, you can use this to build a new group, where somehow the generators of your subgroup become relations of your new group. Okay, so let's do that. Okay, so we're now ready to construct our first finitely generated, not finitely presented group. And so I'm going to let, I've decided to call it K1 for reasons that will not become clear, is to take L and amalgamate it with itself along this K0. Okay, and so this is where I'm going to change my generating set from A and B, right? So the left copy is going to be generated by S and T, and the right copy is going to be generated by X and Y. Okay, and so you know, when you write down an amalgamated free product, you have to specify what the maps are. There's actually many interesting maps of K0 into the free group on two generators, but this one I just mean the sort of obvious one, which takes A to S and B to T on the left side, and A to X and B to Y on the right side. Okay, so now you can write down a presentation of this group. So let's write down a presentation. So our presentation is generated by the vertex groups. It's generated by the edges, but you quotient out the edges in a maximal tree, so we're just going to forget that there's an edge. And then it has the relations coming from the subgroup, which are you set S to the n, T to the minus n equal to X to the n, Y to the minus n for n an integer. Okay, so now I've written down an infinite presentation, right? But now, so why did I sort of go through this whole rigmarole? I'm speaking much, much too quickly. Okay, so please slow me down. This is sort of a habit. So why did I go through this whole rigmarole of defining homology? Well, I've written down an infinite presentation, but now you have to prove that this really is the best presentation. I mean, why isn't this group presented by some better set of relations? Why couldn't I take some smaller set of relations? Okay, and the answer is, you know, it's not, I mean, sorry, I just wanted to like bring up an exercise at this, or sort of an open question at this point, which I think is really crazy. So, you know, I've written down this 4-generator group with an infinite number of relations, and I'm going to prove to you that it's infinitely presented. I'm going to prove to you that you can't do better than this presentation. But here's a case where I believe it's open. If you just take the group generated by 2 generators, so open question, and you add in the relations W that are word to the P is equal to 1 for all W in the free group on A and B, P a prime much larger than 0. The reason I hesitated is because I can't think of a large prime number, but you know, take something bigger than 1,000, and I'm pretty sure this is open. Anyway, is this? It's an open question if this is finitely presented, right? So even if you take this is a seemingly quite simple presentation. You've just taken every word and you've raised it to a p power. We don't actually know if this is finitely presented or not. It might be the case that you could write down some finite presentation of this group. You could maybe do much better than all these words to the p power. You can certainly, I mean, this presentation is certainly not optimal, but who's to say? Okay, so is this p much bigger than 0 uniformly? Let's just say p is a prime greater than 667, so that this group is infinite. So you pick one prime p. This is some presentation. This is the Burnside group on 2 generators. This is a free Burnside group on 2 generators with exponent p. It's an open question whether this is finitely presented. So as far as I know, the techniques that I'm going to tell you today can't help you with this. But actually, I don't know what the second homology of this group is. So who knows? Okay, so let's construct a classifying. So how are we going to show that it's not finitely presented? Well, let's construct a classifying space and compute its homology. Okay, so we can build a graph of spaces, right? So Riley went in, so I'm very thankful. This lecture, the prerequisites for this lecture were really just Riley's lecture course. So I'm thankful that Riley mentioned all of these things. So we can build a graph of spaces, and so Riley sort of said this, and you can check that this will be a classifying space. So if you take a graph of, so let's say you can build a graph of classifying spaces, and it turns out that this will be a classifying space. So it's sort of a small proposition there that I'm not going to prove. Okay, and so in this case, right, we had 2 vertex groups, right, which were both the free group on 2 generators. So vertex spaces will be a classifying space for the free group on two generators, which Radhika helpfully mentioned is the rose with two petals. And the edge space is the covering space Z for K0. Okay, so just recall this is this infinite graph. Okay, and so my space X, so the classifying space for K1 is, so you take, right, so you take a disjoint union of R, Z cross an interval, and another copy of R, and you mod out by the equivalence relation that, so you have a map from, I should label things with different letters. You have a map from Z to the left-hand copy of R, just the covering map. And so you identify Z comma 0 with its image in R, and you identify Z comma 1 with its image in the right-hand copy. Okay, so this sort of looks like you have, so let's draw a very small picture because then I can blame that for the reason that it doesn't really look nice. So you have this sort of, you have two copies of S1 cross S1. You have this space cross an interval in the middle, and there's a map from this end to here and this end to here, and you glue together via those. I think I've probably made that completely opaque, but okay, I think that hopefully you get the idea. Okay, so you're taking these spaces and then you're gluing one end of Z cross 0, 1 to the left hand S1 wedge S1 and the Z cross 1 to the right hand S1 wedge S1. Okay, and this builds a classifying space. And so now we can compute, so now we can use this classifying space to compute the homology, right? So we can compute the, in particular, you know, the thing that I'm interested in is the second homology, but you can use it to compute all the homology groups. And so the trick is, right, it's, you know, how do you compute, sorry, just to go back, what is this space X? You've sort of glued two spaces together along a middle space. And so how do you compute the homology of something like this? Well, you use the Meyer-Vietoris sequence. Okay, so use Meyer-Vietoris where X is, so where A is equal to R union Z cross 0, 1, where this is a half open interval, so it doesn't include the right-hand side, and B is equal to Z cross 0, 1 union R. So you can think of these things, these are really the mapping cylinders. These are the open mapping cylinders of the mapping Z into R. Okay, and so X is obviously the union of these two things, right? And their intersection, if you look at what their intersection is in the space I've described, it's Z cross 0, 1, which is homotopy equivalent to Z. Okay, so I've managed to write my classifying space as something on the left. Oh, yeah. And the mapping cylinder, the point is that the mapping cylinder is homotopy equivalent to the codomain of your map, right? So these two spaces are homotopy equivalent, and they're actually homotopy equivalent to R. Okay, and so now we have sort of everything we need to get going. Okay, so I've written down the Meyer-Vietoris sequence because nobody really wants to see me write down all the terms in a long exact sequence. Okay, but so, you know, you should check that this is true. Okay, and so what are these groups? So over here, I have the first homology of A, which by homotopy invariance is the first homology of R. So this is Z squared. and the first homology of B is also Z squared. The second homology of A intersect B, well, A intersect B is a graph, so it has no two cells. So in particular, it has no homology. And the second homology of A, well, A is homotopy equivalent to a graph, so it has no two cells. Okay, so both of these things are 0. And the rest of the Maya-Viatora sequence going off to the left, I mean, this space X has no cells of dimension 3 or higher. So actually, all of that part vanishes for just that reason. Okay, so now we're left with two terms. Well, this first homology of A intersect B, we already computed. This is the abelianization of K0, which was an infinitely generated free abelian group. Right? So here, I have a direct sum of copies of the integers, one for each natural number. And the group that I'm interested in is the second homology of X. You can compute the first homology of X. I'm not sure that you really care what it is, but if you're interested, then you can compute it from the presentation. It's Z cubed. Okay, you'll see that all of the in the abelianization, all of the relations. In the abelianization, basically all the relations disappear except for one. Okay, so H2 of X is, right, this is an exact sequence. So H2 of X is, sorry, H2 of X is, this map is injective. And so H2 of X is exactly equal to the kernel of this map. Okay, so H2 of X is the kernel of some map, right? I don't really know what it is, and I don't really need to. From here to here, H1 of B. Okay, well, over here, I have Z to the 4, and over here, I have an infinitely generated free abelian group. And so the kernel, I mean, this is sort of a similar application of rank nullity in some sense. The kernel of this map is infinitely generated. Right, so H2 of X. Okay, I'm going to erase this. Is infinitely generated. Okay, so the point being that so you can see this at the level of abelian groups. You're just looking at the kernel of some map from some infinitely generated abelian group, some finitely generated abelian group, so you have to have something infinitely generated. Okay, so in particular, so now we have a finitely generated, not finitely presented group, right? Exactly this group, which is an amalgamated free product of two free groups. Now, as I said, you know, if I was to tell you that this was the whole story, you should, if I was to end the story here, you should leave with a very unsatisfied feeling. And you should really come up to me at some point and ask me, well, where did this group come from? Why did you why did you just arbitrarily start amalgamating things? You know, why this group, right? There are many ways to construct not finitely presented groups. Why did you pick this one? And the reason I picked this one is that we can do something nice. And namely, what we can do is we can embed it. So let's embed K1, which is L star K0L, in a seemingly, say, nice group. Where, as in Davide's talk, the definition of nice depends on who you are. And depending on the day, I think that the group we're going to embed it in is lovely or absolutely horrible. Okay, so let's embed it in a nice group. So the point is that K1 has two homomorphisms to L. Okay, it has two homomorphisms to this free group on two generators that I want to tell you about. And so first, we have a map psi, which goes from K1 to L, which sort of I like to think of as folding. So what do? You have this, so in K1, you have this left-hand copy of L, and you have this right-hand copy of L. So take a map, take the identity map from those copies to L. They agree on K0, and so you get a map from the push out, right? And so to write this using the algebra of presentations, map S and T to A and B, and map X and Y to A and B. Okay, so you're taking your two copies of L, each one is identified with your copy of L generated by A and B, and so you're sort of, the way I like to think about this is that in this amalgamated free product, you have L star K0L, and you're just folding these two copies together. You're just folding this whole picture in half, and you're just saying, okay, let's look at this sort of folded thing. Okay, so so this is in general something you can do if you have what's known as a double of two groups. So if you have a group amalgamated with itself along a subgroup, you can just fold and sort of leave this subgroup to its thing. The other one is, so the second comes from quotienting by K0. Now K0 is normal in K1. This is, I'm inclined to say that this is an exercise. Did I decide to write down? No. Okay, so, well, I mean, so K0, sorry, K0 is normal in K1. So you just have to check, right? If you conjugate by S, then because K0 is a subgroup in S, a normal subgroup of the group generated by ST, you remain in that side, and similarly for TX and Y. Okay, so the point is that if you look at K1 modulo K0, you can write this as L modulo K0 star L modulo K0, and really in the middle here, you're amalgamating these two things along K0 modulo K0. Okay, so once again, you can do this whenever you have a normal subgroup. If you take a group and you amalgamate it to itself along a normal subgroup, you can just quotient out by that normal subgroup, and you get something that looks like this. You can do something more general, but for you to get something that looks like this. Okay, and so this is equal, right? So this is just equal to a free product, L mod K0, right? But K0 was the kernel of a map to Z. So L mod K0 is just Z. So this is just the free product of Z with itself, which once again is a copy of L. Okay, so actually you can see this map on the level of generators. So on the level of generators, you have this map K1 to L, and what this does is instead of folding these copies together, it sort of sends the left-hand copy generated by S and T to this Z, and it sends the right-hand copy generated by X and Y to this Z. Okay, and so by the universal property of the direct product, or I always say it like that, but that maybe just sounds more grandiose. Okay, just think about if you have a map from G to H and a map from G to N, then you get a map from G to H cross N. So we get rho, which is a map from K1 to L cross L. Okay, and you're just going to take some X in K1. So you're going to take some word in K1, and you're going to map it to psi of W, comma phi of W. Okay, so you just take an element of K1 and you map it to the element which is the tuple consisting of these two words coming from these two maps. Okay, now the point here is that it turns out that this map is injective. Okay, so rho is injective. Okay, and this isn't, if you think about what the kernel is, right, the kernel of rho is the intersection of the kernel of these two maps, right? But what's the kernel of phi? Well, phi was quotienting out by K0. So the kernel of phi is equal to K0. So the kernel of rho is equal to K0 intersect the kernel of psi. Another way of saying this is that this is the kernel of psi restricted to K0. Okay, but if you looked, right, psi was injective when you restricted it to either side. Okay, it mapped S and T. So let me just go back 2 pages, right? It mapped S and T to A and B. And so in particular, if you just restrict to the subgroup generated by S and T, which is a copy of L, then this map is injective. Now K0 is a subgroup of the thing generated by S and T. So in particular, it's injective when it's restricted to K0. Okay, and psi restricted to K0 is injective. So the kernel of rho is trivial. Okay, so now you have a homomorphism from this sort of random, finitely generated, not finitely presented group that I just constructed out of the blue in some sense. Okay, but now you've got a homomorphism to a product of free groups. Okay, and so this leads you to the theorem, and so this is sort of the start of the whole world of Bieri-Stallings groups. So this leads you to the theorem that F2 times F2, I should have just used F2. I wasn't going to talk about finiteness properties. L times L is incoherent. Okay, so this is sort of a great start. And in fact, K1 is really the kernel of the map from L times L to Z, which sends, let's say that this is generated by A, B, C, and D, sends all these generators to 1. Okay, so really K1 is actually the kernel of some map. It's really the same way that you got K0. And so when you took one copy of the free group, you got something not finitely generated. When you took 2 copies, you got something finitely generated, not finitely presented. Turns out if you take 3 copies, you get something that's finitely presented, but whose third homology is infinitely generated. And I've sort of outlined how you do this on the problem sheet in a way that lets you sort of bootstrap this up to construct groups with any sort of interesting level of generation of homology that you like. And actually, there's a lot more to be said there. And there are some amazing results about what possible things you can get as the homology of finitely presented groups. But okay, so let me pause for a second here and ask if there are any questions. No, the image of rho is infinite index. In particular, it's an integer's worth. Okay, so okay, so now I've embedded my finitely generated, not finitely presented group into a product of 2 free groups. And now the great thing here is that now sort of one actually really quite big tool for showing that something's incoherent is just show it contains a product of 2 free groups. Okay, you don't have to look for a crazy subgroup that's not finitely presented. You just have to look for what is very simply a product of 2 free groups. Okay, and so here are some, so we can actually do this in the cases that Radhika mentioned in her talk. So I've written these out. I thought that I would take longer to say all of this. So now for tomorrow, I'll know how much say. But okay, so the first example, right? What Marissa was talking about, the mapping class group of a surface. Whoops. Okay, so if you look at the mapping class group of a surface, right? As long as the genus is at least 2, and we've already seen that if the genus is 1, then then you get SL2Z or GL2Z, and there's some small number coincidences. If you take these 4 curves, take 4 curves in this configuration, right? You can always find these as long as the genus of your surface is at least 2, right? Then it turns out that, well, it's obvious that so I think that Marissa went through why this is true, but if you take the Dane twist about alpha 1, that commutes with any Dane twist over here, right? These things are just supported on different surfaces. And so you can see that alpha 1 commutes with the subgroup generated by alpha 2 and beta 2, and similarly for beta 1 and alpha 2 and beta 2. What's slightly harder is to see that if you take fourth powers, I think third powers might be enough. Somebody, does anyone know if that's true? Then actually, the Dane twist about alpha 1 to the fourth and the Dane twist about beta 1 to the fourth generate a free subgroup. So actually, by taking fourth powers, this subgroup I've written down here is a copy of L times L. Okay, so these are incoherent. And for genus 1, I think other than a few sort of, you can also do this for not closed surfaces. And I think, you know, as long as the complexity of the surface is high enough, then you get incoherence. There's some, like anyway, okay, I don't want to mention that right now. Okay, so mapping class groups, right? Incoherent, and the proof is really you just embed F2 times F2, okay? Secondly, the automorphisms of a free group. So you can either take the automorphisms or the outer automorphisms for n at least 3. And once again, in the case that n equals 2, the outer automorphism group is a virtually free group, and coherence is virtually free groups are coherent. We'll talk about that later. But for n at least 3, you can do you can define these automorphisms. So let me erase. Do I want to erase this? Maybe I don't. Maybe I just want to explain what these things are. So for n at least 3, you take the automorphisms which fix every generator except for the nth one. And on the nth one, what they do is they multiply on the left by some word in A1 and A2, and they multiply on the right by some potentially different word in A1 and A2. Okay, it's not too hard to see that these automorphisms are going to generate you a free group, right? There's a the natural map which sends sort of A1 to left multiplication by A1 on AN and A2 to left multiplication on AN by A2 is a free group of rank 2, and the right-hand side thing is also a free group of rank 2. And obviously, if you're doing something on the left and something on the right, then these things commute. They're not interacting with each other in any way. Okay, and so this is a copy of L times L, and so you have a product of 2 free groups, and so this is incoherent. And so right, so I've done this in the automorphism group, but you can see that this subgroup I've written down intersects the inner automorphisms trivially. It's a small exercise. Okay, so the quotient to the outer automorphisms is an isomorphism on this subgroup. Okay, so and you can sort of see why I needed n at least 3, right? I mean, I was sort of using A1, I was using A1, A2, and some other letter. So I needed n at least 3. And then my sort of final example where this really works is SLNZ for n at least 4. Okay, so for SLNZ, I mean, the point here really is that you can embed SL2 cross SL2. And here are 4 4x4 matrices that genuinely generate a free group cross a free group, right? You can see, so somebody mentioned this. Okay, somebody mentioned this last week, that these 2 matrices generate a free group. Okay, and so you have these 2x2 matrices that generate a free group, and then you're just the identity outside of that. And so you put that in the top left, put that in the bottom right, sort of everything from the left side commutes. Oh, okay, it was Riley again. Yeah. If you missed Riley's course, then I have a lot of explaining to do. So the two generators on the left-hand side commute with the 2 generators on the right-hand side, and the 2 generators on the left-hand side generate a free group. 2 generators on the right-hand side generate a free group. And so once again, you have a copy of L cross L, and so you're incoherent. And so actually, you know, this really is a great way to show incoherence. I mean, another, you know, so you know, you can just take products of, if you take products of hyperbolic groups, right? That's going to be incoherent as long if you take a product of two non-elementary hyperbolic groups, you're going to have an F2 in each factor, and so you're going to have an L cross L. To answer the question in the chat, it is an open question. Thanks, Sammy. So so I'm going to mention this along with a lot of other open questions, but it's a completely open question what happens for SL3Z. So it is known that you can't embed a copy of the free group across the free group. So this proof I've shown you today cannot work for SL3Z, but it's not known if it's coherent, and it's not known whether that's enough. So I think I'm going to end there and just open it up to questions a few minutes early. So thank you all very much for listening.
Thank you for the great talk.